There are still seats up front. Good. We've got a full house, and I don't see anybody running down the hall, so now is a good time to. Okay, almost nobody. Now is a good time to get started. So I'm very pleased to have Manxi Wu giving today's SCAM colloquium. Manxi did her PhD at MIT and then was doing something with Simons and was at Berkeley EECS for a postdoc and just came here this year, or was it just this year or last year? Okay, just this year. That's what I thought. Yeah, I works on a variety of interesting things relating to transportation, general optimization, and today is talking about autonomous carpooling markets. And with that, take it away.
Okay, thanks David for the introduction, and thanks everyone for being here on a Friday afternoon. So the title of my talk is Spatial Temporal Toll Pricing for Autonomous Carpooling Markets. Here is today's agenda. Since this is the first time that I speak to the CAM community, I want to give a short overview of my research agenda, and then I'm going to focus on one paper that I recently just wrapped up on this topic, and this is a work that I started at the end of my PhD and spent some time in my postdoc as well as in the last summer to work on it. This is joined with two professors from MIT, Saurabh Ami and Patrick Gandhi. Okay, so I believe this is a very exciting era to work on urban systems. With all the technology advancements from the relatively more matured ones on navigation services to what has transformed drastically of how we live and how we commute in the past 5 to 10 years on the ride sharing and ride hailing, and what is currently happening as a full adoption of electric vehicle at societal scales, and something that is maybe more futuristic that hopefully we will embrace the age of autonomous driving in the near future. So all these technologies are great, and they provide different information and services to human users. The goal of inventing these technologies is to move our society to achieve various of societal goals and to serve the people as well as the urban systems. These platforms and technologies reshape the information and incentives and reshape the aggregate behavior on how people make use of the resources in urban systems. On the other hand, these technologies and services consume the capacity and resources of the network environment of the urban networks, and also it heavily relies on the availability of the data, the ability to collect data at different locations of the network, as well as the computing power of processing them and forming prediction or decision-making problems. So things are not always rosy or promising. As I have mentioned, how the technology is serving the society depends on how people use it. And in fact, we have seen some troubles actually raised by the new services. For example, the navigation services is believed to could sometimes congest small neighborhoods due to sending too much traffic there during the morning rush hour. And Uber and Lyft, although made our life more convenient on-demand transportation, it actually drives riders from the public transportation systems and sometimes can create significant proportion of congestion during the rush hour in urban area. This is because the new technologies and services can sometimes misalign between the individual incentives and social welfare. So incentive is the key word of how people use these technologies. On the other hand, people get very excited about autonomous driving, which is believed to make our traffic flow more smooth and to have a more safer and as well as higher throughput in urban networks. But there is also another study by Berkeley CE Professor John Walker that shows that when people are provided with free driver that is on call 24/7, they actually showed by a study that people have significantly increased the travel demand. And this is probably is what is going to happen. Although autonomous driving relieves people from the burden of driving themselves, it doesn't drastically improve or increase the capacity of the physical infrastructure. And therefore, how much traffic can go through the system and how people experience when they travel still is constrained by the physical infrastructure. Well, just to briefly mention several other factors that need to be considered. For example, traffic incidents, the failing and aging of the infrastructure facilities, natural disasters, as well as some security attacks of the increasingly adopted and inserted control as well as data transmission units in our urban systems. So all these things motivate me to try to use my work to answer two questions. The first question is, what is the real impact of these AI technologies as well as services? In particular, how do they really reshape people's behavior and how does it affect the usage of people on the public resources in urban systems? Second question is, based on the understanding of human behavior and these technologies, can we leverage the new technologies as well as to design the correct and proper incentive mechanisms that will reshape the usage behavior so that we can put the technology in the right place and achieve a better societal outcome? So to answer these two questions, I believe three key components must be considered in the framework. The first one is the technology that provides information, services, and provides incentives. Second is human decision maker that includes the users and system operators who will have their own incentive, their own goal of utility function. The third aspect is infrastructure that is prone to failure, either random or strategic uncertainty, and it has its own physical structure and capacity limits. Because of these three key components, and we need to understand the interaction among them, I propose the following analysis framework. On one hand, we need to understand the human behavior as well as the goal of the institution. That encourages me to adopt and build on foundational tools of game theory and mechanism design. On the other angle, to really grasp how the engineering systems work, we need to analyze the dynamics of the system as well as the network structure that encourages me to use tools in optimization, control, and machine learning. To put them together, these are the two things that will keep me busy in the next 3 to 5 years. The first is to, hopefully, the first is to analyze the strategic interactions of human agents under the technological and physical constraints in the infrastructure networks. And second is to, based on this understanding, to provide information and incentive mechanisms that improve the efficiency, sustainability, resiliency, and fairness of our urban systems. So a brief summary of my past and some of the ongoing work. The main chunk of my work falls under the spectrum of applied theory, where I use mathematical modeling and analysis tools to understand the information and incentive design problem in urban systems. I have worked on studying the value of information provided by navigation apps in routing gates, and how to do information design to improve the traffic congestion. I also worked on market design for incentivizing efficient carpooling. Slightly moving towards more on the theoretical angle, I have worked mostly on learning in strategic environment that includes the belief, strategy learning in continuous games, multi-agent reinforcement learning, and some of the recent work for learning and exploration in networks. Some of my recent research interest is doesn't have much theory, but focuses more on the data and the communication aspect. I have worked on the problem related to how to use machine learning methods to predicting the aggregative mode choice in the San Francisco Bay Area. And one of the work I'm currently very excited about is to how to use a data-driven approach to design a fair tolling system for the Bay Area. So I will, for the rest of today's talk, I will only talk about the market design for incentivizing efficient carpooling. If you're interested in the other works, feel free to shoot me an email and then we can talk. Okay, so let me dive in. When can I see the time? Okay, I can't really see the time. So, but just tell me if I'm running out of time, and then I will just. Okay, great. So let's dive into this paper. This paper considers about how to incentivize carpooling in the future mobility platforms to efficiently use the resources in network. And the network infrastructure of our highways have limited capacity. So one key factor here is that autonomous driving is going to release our burden of being a driver. And when we order, for example, a car service from Uber, a lot of the payment that we pay goes to the driver's salary and compensation. But without the driver's cost, whenever the system scales, the cost of using autonomous driving service is going to be cheaper than what is currently the case. Well, people wonder whether or not autonomous driving is going to solve the congestion problem. My answer is that it really depends. If people are willing to form carpool and efficiently share the network capacity, then we will have less vehicle miles traveled, less congestion, and less pollution. However, if all of the people decide to increase their travel demand and to take solo trips, to employ an autonomous vehicle and to take on a solo trip, they are going to exceed the capacity limit of the network, and that will cause congestion as well as more pollution. So the research question I'm trying to answer here is how to incentivize riders with heterogeneous preferences to take carpool trips and share the network capacity efficiently. Just a simple thought process. If we set the toll price to be 0, which means it is free to use a lane of a road segment at a particular time, then people would favor the convenience. They would like to take a solo trip, and when they will want to take a solo trip as well as use the route that is the shortest path to their destination. This will create a huge amount of demand on these network shortcuts that can exceed the capacity of the route segment. On the other hand, if we set the toll price to be high, then either one of the two cases would happen. One is that people may start to switch to slightly longer road, depending on their willingness to pay and their value of time. Or they would form carpool trips so that they will still take the short paths, but they are going to divide the toll prices through some payment mechanisms among themselves, and they will arrive at the destination at a relatively low cost and as well as a shorter time. So the economic insight behind this spectrum is that the toll price is actually an invisible hand that balances the demand of trips and the supply of road capacity. So before going into the detail of the model, I want to talk about our contribution and results at a high level. We consider the case where there are a set of riders with heterogeneous preferences that want to take trips in a road network. The road network is set with a toll price, and based on the toll price, the riders will form carpool trips and then split the cost of the trip. That includes maybe the gas and fuel, as well as the toll payment, among themselves in a certain mechanism. This can be either decentralized or can be here that I introduced a market mediator called the platform that would collect the payment, raise the toll price, and organize the trips on behalf of the travelers. Here, our focus is a competitive carpool market. This is inspired by a previous work by Michael Ostrowski and Michael Schwartz in 2018. But the difference is that we really emphasize on the network structure perspective as well as the temporal aspect of the dynamic travel demand. And based on this competitive market, we provide sufficient conditions. We look at the equilibrium concept of the market, and we find that it may not always exist because of the network and integer constraints. So we look for sufficient conditions that guarantee the existence of market equilibrium. We find polynomial time algorithms for computing the optimal trip assignments, payments, and toll prices at equilibrium. And we also discuss how such equilibrium can be implemented through platform. So that is about which equilibrium, can we find an equilibrium that is strategy-proof and maximizes riders' utility. So if you're not familiar with the concept of competitive market or equilibrium, don't worry. I will talk about, I will explain all these terminologies in later slides. Okay, so just take a high-level look of this problem. The problem has two aspects. The first one is we need to solve a trip assignment problem that is a large-scale combinatorial optimization problem. That when we think about the carpool trips, we need to decide what is the set of riders that are going to share a carpool trip, that are going to sit in one car. And second is when they are going to depart and which route they are going to take. So that is the dynamic flow of the problem. It's not just about this integer optimization problem, because although integer problems are hard, there are various tools and theories that allow you to find a very good approximation algorithms and solutions. But here, since people have their own preferences and they have heterogeneous preferences, if you really want them to follow the organized carpool trips, you need to find a payment and a toll price mechanism that satisfies incentive constraints for riders with heterogeneous preferences. These two sides, one on the optimization, the other side of incentives, makes this problem challenging. We developed an approach to tackle the form rider group problem, the form coalition of rider problem, using the combinatorial auction theory. And on the other hand, it turns out that the dynamic flow, which means how the network resources of routes as well as the departure time is being used in the optimal solution, is relevant to the earliest arrival flow problem. And of course, this work contributes to the line of literature on carpooling and shared mobility. And in all three areas, there has been a lot of wonderful previous work done by the Cornell students and faculty. So in summary of the contribution is that it turns out that ideas combined from the combinatorial auction theory and the flow problem can be applicable to design an incentive mechanism for resource sharing in a network environment. Let's go into the model. We consider a network with a set of edges. Each edge has an integer capacity, and there is a travel time of how fast you can go from the start to the end of this edge. And given the edge, the route is a sequence of edges that connects the origin to the destination, and you can compute the travel time as the sum of the travel time of all edges. So a carpool trips, a finite set of riders come into the system to demand a carpool trips in discrete time interval from 1 to capital T, finite time interval. A carpool trip is defined by three aspects. First is the departure time of this trip from the origin. Second is the subset of rider group who shares a vehicle. The third one is the route this car takes. So when a route is taken by a trip, it takes 1 unit of capacity on all edges belonging to this route. So the feasible trips need to satisfy two conditions. One is that the size of the rider group should be smaller or equal to the vehicle capacity. And second is, given the departure time plus the travel time that is needed, it needs to arrive at a destination no later than this time horizon. Okay, so we represent the trip organization vector by this long vector, where XRZB basically equals to 1 if the trip with departure time z rider group B, and using route R is being organized, and 0 if otherwise. So you have exponential dimension of this trip organization vector, and they're either 0 or 1. So they're binary. The trip organization vector will determine how limited edge capacity is shared spatially as well as temporally. So now it comes to the riders with heterogeneous preferences. Rider M has a value of, so rider M's value of a trip that includes him, so B that the rider group includes M, is given by this following function. Let me break it down. So alpha M and beta M are about the value of arriving at a destination and minus the value of time multiplied with the time cost of taking this route R. And then the second term concerns about the arrival time. So we know the trip is determined by the departure time and the route it takes. So Z plus TR equals to the time that the trip arrives at the destination. But player M may have a latest arrival time that he or she would like to target at. For example, that's the first event of the day for the work. And there will be a penalty if the arrival time is later than the targeted arrival time. And this is the delay cost of arriving late. And third aspect concerns about carpooling. Here we consider the case where there is a linear cost of carpool. This and both the intercept as well as the slope depends on the size of the carpool. So essentially, there is a fixed carpool cost that may arise from, for example, the need to share the space, the lack of privacy, the need to walk to a pickup or drop-off location, as well as maybe the potential detour that needs to happen because of the carpool. So this is summarized by the intercept as well as the slope of the carpool distribution. And it increases as the carpool size increases. Yes,
So
please.
TR is the time of arriving at the destination of the rider M. There are many destinations, presumably not all the riders have the same destination. So which one is TR?
TR is the route that the trip takes. Yes.
To the very end. So if the ride drops me off as the first customer to get home.
So here we consider origin as a region and the destination as also a region. So there are a set of people roughly in this area being picked up and then dropped off at this location. So you can consider this network as a single or D pair, but you may have detour that happens at the pickup as well as the drop-off. That is summarized by the cost. For example, the fixed cost. This may be different for different people. But here, since we can focus on the market and system level, we kind of didn't model the detail of how the carpool trip is picking up and dropping off the person.
So they're sort of assumed to share the pickup and the destination, but there is an extra cost for many of them around that destination.
Yes. So that's why like this utility has a part that scales with the driver size and another part that scales with both the driver's size as well as the time that you need to spend on it. Yes.
On the same point, are all of these being treated deterministically or?
Deterministically, but the platform may not know about it.
Okay.
Yeah. So if a person will not be able to report the entire function, that would be too much. But what they can report are their features of preferences as a parameter.
But something like late arrival is not treated as a random variable.
Late arrival is not random variable. It's determined by when you depart. So like if you depart at if you decide to take a carpool trip that departs at 8 a.m. and then it takes 30 minutes to arrive, but your first event is at 8:15, then you are 15 minutes late. And every person has a penalty that is specific to themselves based on how late they are. Yeah, thank you. I think.
So just a clarification question, like, so what is preventing, what is enforcing that the route R picks up and drops off everyone in B? It seems like from your last term, the route that you take and the group that you're serving are assumed to be independent of one another?
Yes, because I'm considering a large group of people, for example, people who want to travel from San Jose to San Francisco. I'm having the origin as the San Jose and the destination as the San Francisco. People may have different places, but I consider them to be the two abstractive nodes. And then I care about, for example, whether I'm taking 101 or I'm taking 280 as a highway. Exactly in the city, what sequence am I being dropped off? That is considered as the disutility of the possible detour, right? So when when the size of B equals to 1, which means I'm taking a solo trip, then I will not have this cost. Okay, great. Thanks for the clarification questions.
Also, that is a function, right? In
Which
terms
is
of like pi m, there's a bracket.
Yes, so that means I do not actually care who I'm carpooling with. I only care about how many people I'm carpooling with. Yeah. Because the more people I carpool with, the more possible detour I would experience and the more lack of privacy I would endure. Yeah. Okay, thank you. Okay, so the social value of a trip RZB equals to the sum of all the riders in that trip for the value function minus the cost of the trip. We have an assumption that the cost of the trip is linearly increasing in the distance, in the route that it takes, for example, that governs the energy consumption of the vehicle, as well as the wear and tear. And also it increases as the size of the route. Okay. So what is the optimization problem? Since we mentioned that as one aspect of the problem, is to maximize the total social welfare of this trip organization subject to two constraints. The first constraint that is each rider is only assigned to at most one trip, so the feasibility of for riders. Second constraint comes from the feasibility constraint of the network capacity. So here, I'm summing over all the trips that will enter a particular edge at a particular time t. And I require that it induce the dynamic flow that enters an edge at the beginning of the interval t must be smaller or equal to the fixed network edge capacity q. And this constraint holds for all the edges as well as for all the time interval. So this is a dynamic network flow constraint. And of course, we want trips to be either organized or not organized. So this is a very challenging integer optimization problem. And second aspect, we want to consider the market. And here I'm going to introduce the market equilibrium. The market is that riders with heterogeneous preferences are served with trips, and then they need to pay. They need to pay for their trip. The payment of their trip will cover partly the toll price. And the toll price, look here, is spatial temporal because for every edge you have a toll price, and this toll price can change with time. So the payment will need to cover the toll price as well as some of the cost of the trip. So the market outcome is summarized by three elements: how the trip is organized, what is the payment of every player, and also how the toll is being set for each edge and each time interval. It needs to satisfy a set of conditions. First is individual rationality, which means given this market outcome, the rider's utility must be non-negative so that nobody wants to quit from this platform. Here we kind of normalized to the alternative of no traveling as the utility being 0. Second is budget balance. So for any trip that is being organized, it must be that the payment collected for riders within that rider group should equal to the toll price along the path that they take. So look here, I sum over all the edges, but I also adjust the toll price based on when I'm arriving at the beginning node of each edge as I proceed through this route, and plus the cost of this trip. So I'm budget balanced. The third constraint is stability. To make sure that people are happy with the organization, one condition is that there will be no subset of riders who want to organize a different trip of their own. And this takes a little bit time to process, but I'm going to say here that in short, this means that there will not be a subset of riders who organize a trip themselves, given the toll price as well as the cost of the trip. They cannot find a way to divide this cost in a certain way that makes each and every one of them better off. And this includes any subset of riders. Of course, it will also include one rider decides to break from the carpool and take a solo trip by themselves. Okay? And this needs to hold for all the trips. The fourth one is market query. So that means if an edge is underused at a particular time t, then there should be no toll price, because the resource of that edge at that time t is not being exhaustively used. So this is market querying for all edge as well as for all time interval. So let's look at the problem of the market being intermediated by the platform. The platform faces two questions. First is, will riders follow the assigned trip and also pay their payment? The answer is yes, if and only if the platform is implementing a market outcome that is an equilibrium, so that people actually are willing to take it, they will not break it, market clears, as well as they will not leave the platform, and also it is sufficient. It's budget balance. So, to the first question is yes, if it is a market equilibrium. Second question is, well, the platform may not have knowledge about riders' preferences, right? So the platform will rely on the riders to report their preference parameters. So that is the value of the arriving at destination, value of time, and these utility parameters about forming carpools, as well as their preferred arrival time and what happens if that is late. So you will want to find an equilibrium that is called strategy proof. That basically means that the platform needs to execute a market equilibrium such that no rider can achieve better utility by misreporting their preferences. Because the platform actually doesn't know the preference of the rider, and they need to entice this information from their users. Okay, so I guess many of you will wonder why autonomous driving, right? So in my model, which part really talks about autonomous driving? So I want to mention mainly answer this question from two aspects. The first is that, well, I have to say, this model can be easily extended to carpooling markets where there is a driver. But the modification or the justification that you need to use is that you need to consider the compensation of the human driver as a part of the trip cost. However, I do believe that a competitive carpool market is most suitable to be considered for autonomous carpooling because of the technology complementarity between three things: the autonomous driving, the carpooling technology, as well as the micro-tolling. So autonomous driving will be able to enable much reliable, on-time, and frictionless carpooling services. And second is automated tolling is becoming cheaper and more flexible. And in fact, this spatial temporal tolling for every edge is implemented in quite a large region in Singapore, where reducing congestion is their city's priority. And second is that I believe toll pricing becomes a lot more important when autonomous driving is being adopted. Right now, the driving demand is largely restricted by the availability of the driver or the people's time availability of driving themselves. However, when there is no need to request a driver, it is more about the infrastructure capacity. So this competitive tolling market will become critical to avoid the congestion caused by autonomous driving. Okay, so before I dive into the technical results, I'm going to pause here to take questions about this framework as well as the model. Yes, please.
So, your pricing conditions ensure that individuals will not look for any other alternatives, and thus will not impact the congestions or the limits of usage of the individual edges. Is that correct?
Yes, so it respects the incentives of people, and it also respects the capacity constraint of the network. So here, instead of the congestion function about travel time changes with the number of cars, I actually used an L-shaped function. So when it is below the capacity, it is almost the same cost, and when it increases, it becomes infinity. So it's a hard capacity constraint, as how many vehicles can enter an edge simultaneously at the same time.
I understood this part. My question
yeah.
is, you assume that they will not quit your system and start driving themselves, for example?
They will not.
Changing the capacity constraints for everybody else. Okay.
No, they will not. So this is guaranteed by individual rationality and stability. Because the scenario you talked about is basically the subset of rider who wants to deviate. It's just one rider who wants to take a solo trip. So that is included by this constraint. Yeah. Thank you. Yes, please.
So is stability, this concept you mentioned, as those in cooperative games?
Oh, this is more used in cooperative games.
Yeah, I mean cooperative.
Yes, it's a stability constraint for coalition formation. Yeah. Okay, thank you. But here you need to consider the route and departure time slot. Yeah, thank you. Okay, so 3 things: existence, computation, strategy proofness. Let's dive in. So we need a structural way to understand the existence of the market equilibrium. For people who are familiar with competitive market theory, there is no surprise that actually a competitive market can be represented by the primal, the linear relaxation of the socially optimal trip organization problem, as well as the dual program. So here, the left-hand side is basically I'm just relaxing this 0, 1 to a trip being larger or equal to 0. And the dual program is basically I introduce the dual variable um for every rider's constraint that represents the rider's utility, and the toll price, toll et, to every of the capacity constraint of every edge and for every time interval. And this primal and dual program turns out to be that the 4 equilibrium conditions is equivalent to the primal feasibility, dual feasibility, and complementary slackness conditions for the primal and dual problem. So this actually tells us that market equilibrium exists if and only if the primal linear relaxation has an optimal integer solution, so that we are guaranteed to have the strong duality. So this first result tells us that to look into whether or not market equilibrium exists, we boil that problem down into looking at whether or not the linear relaxation is equivalent to the original integer problems. And actually, this also provides us a way to compute the utility, well, which is equivalent to the payment, as well as the toll price that supports this trip organization. When market equilibrium exists, the integer solution of this LP relaxation is the feasible and socially optimal trip organization. This is actually a result of the first welfare theorem. However, when the LP is not equivalent to the integer program, because of the integer constraints of the original problem, your market equilibrium will not exist, you will not have stability, and you will not achieve social optimality. So okay, we turn the problem into the equivalence between LP and I. The second is we look at the LP problem and try to figure out conditions of this model such that this LP is guaranteed to have an integer solution. Turns out that you need 2 conditions. One is that the network is series parallel, And second is that the carpool disutility parameters are homogeneous, non-negative, and non-decreasing in the group size. In this case, your LP will have an integer optimal solution, and then you can have a polynomial algorithm, which I will mention later, that solves both the primal and dual problem and gives you a market equilibrium. So I will talk about two things. One is how to interpret these two conditions, and second is how the proof would actually work. Well, actually, you can find counterexamples where market equilibrium does not exist when either one of the two conditions are violated. The first one is a Wishbone network, so this is not series parallel. And even with zero carpool disutility, which means the second condition is triply satisfied, but actually it can find examples where market equilibrium doesn't exist on this network. The second is on a parallel two-link network, which is very simple in the network topology, but you can find heterogeneous carpool disutility of 4 riders and in a 3-seat vehicle such that the market equilibrium also doesn't exist. I'm not saying these two conditions are necessary. They are sufficient conditions. They are somewhat necessary in the scenario that you can find incidents, you can find examples where when they are not satisfied, actually equilibrium doesn't exist. But of course, we can also find examples where they are not satisfied, but they exist. Okay? So the implication of the series parallel network condition is that if you want to consider this competitive carpool market, it is better if you set dedicated lanes that avoid embedding the Wishbone network in order to install the tolling and carpooling facilities. So this is actually part of the reality for some of the highways. For example, the 101 highway system in Bay Area, they do not, so although the network structure may be complicated, but actually the carpool lanes as well as the tolling lanes are set for a dedicated direction, for a dedicated stretch of the highway. So if you just look at the carpooling and the tolling lanes, they actually have a simpler network structure compared to the entire highway infrastructure. I do want to mention that this condition becomes necessary only when the tolls are set off edges. If you have more advanced technology that can anonymously toll a vehicle based on the routes it takes, that may not be the sum of all the toll prices of the edges that it takes, then you can actually remove the series parallel network condition. Second is, what does it really mean by making the condition of homogeneous carpool disutility? So first, I want to say that riders can still have very heterogeneous preferences about their value of the trip, value of time, about their latest arrival time, their delay function cost. It's just that they need to be homogeneous about how much they do not like about carpool. Okay? So this actually is reflected in the current design of the ride-hailing system. For example, Uber provides service of solo trip as well as for the carpool, but they are separated as two different markets. All I want to say here is that a platform can still service people with different level of carpool disutility, but they need to create a separate sub-market for different populations. And riders will roughly be pulled together with people who have the same level of carpool disutility. That's how I interpret these two conditions. And they are served with different classes of services that may range from solo trip only to 4-seat vehicle to 10-seat minivan or to a public transportation. So different service class actually ranges from solo trip to the current public transportation systems. Okay, so the proof idea. Actually, how much time do I still have?
It's 4:30. We should wrap up by 4:45. You might want to be 5 minutes early.
Oh, okay, sure. I think I still have some time there. Okay, great, thank you. So the step one is to first construct a dynamic flow. So just forget about grouping riders into carpool groups. We just think about, given the network capacity and the network topology, how we want to allocate the edge capacity into the capacity of routes as well as the departure time slot. So we are doing this using a greedy algorithm first to construct a static network flow problem. I'm going to start with not picking any route, and then I'm going through all the routes by selecting the route, the currently available route with the minimum cost. And then I'm going to allocate the maximum capacity that saturates this route. And I'm giving this route allocated with the saturated maximum capacity. And then I move on to the next shortest path that still has residual of the capacity. This is a static assignment of edge capacity to route capacity. But we consider a dynamic flow. So we construct a temporally repeated flow where basically I'm allocating time capacity for every time slot on all the routes according to this static capacity. But I can only do that until t, capital T minus TR, because I need to guarantee that through this route, given the last available departure slot, I'm able to arrive at the destination before time capital T. So, well, the first lemma we show is that we construct this more restricted LP. So this LP is the same with the previous LP except for this constraint. So previously we say that the trip organization needs to satisfy the dynamic network capacity constraint. But here I'm saying that actually the number of vehicles that you send to use route R starting from departure time Z must be smaller or equal to my allocated route departure time capacity according to the computed temporally repeated flow. So this is a more restricted LP, so the optimal solution should be a lower bound of the previous original LP. But actually we can show on series parallel network, this LP is equivalent to the previous one. So it's not a lower bound, it actually gives you the same optimal solution. The way to show that is actually by constructing any optimal solution of the original LP and do a reordering of the assignment of trips to route and departure time so that this constraint is satisfied according to the computed temporally repeated flow, and still show that you are not decreasing the objective function value. But this only holds on series parallel network. On the Wheatstone network, I can easily construct examples where the temporally repeated flow is not the optimal way to construct the rolling capacity. And the market equilibrium actually doesn't exist, which means the previous LP doesn't have integer solutions. Well, this solves the problem of the route and departure time slot. The second question is, how should we allocate riders to these slots? Here I construct an auxiliary economy where actually riders become the goods in that economy, and the route and departure time slot becomes an agent. So the incentive is actually reversed, but they're economically totally different, but they're mathematically equivalent. And rider's utility becomes the good price. What I show is that the socially optimal trips as well as the equilibrium utility on the restricted LP is equivalent to the optimal allocation and equilibrium price for this economy with indivisible goods. But there is a caveat here. You cannot do the same, do this equivalence right away. You need to construct something called augmented trip value function. It is because for our trip, we do have a constraint on how many riders can sit in a single vehicle. But in good allocation problem, usually you have the assumption of free of disposal. So we construct some augmented trip to satisfy this monotonicity condition. Then we find that with this augmented value function, if riders have homogeneous disutility parameter, then the augmented trip value function actually satisfies a condition called Gauss substitutes. Under the Gauss substitutes condition as well as the monotonicity condition, the equilibrium exists in the auxiliary economy, and that equilibrium can be mathematically shown to be equivalent equivalent to the optimal trip organization as well as the equilibrium utility for our original problem. So in this way, we showed that in 2 steps, we showed that we have an optimal integer way of allocating capacity. And the second step, we showed that we have an optimal and integer way to group riders to take those route and departure time slots. So 2 steps combined, we showed that the theorem holds. Yes?
In step 1 of this, of step 1, maybe I'm misunderstanding something. What is preventing you from picking an empty route? You're finding one with minimal cost, but I'm confused as to like where that route is starting from and where it's going to.
Oh, so I'm going to show it with an example. Okay. Thank you. Because the algorithm of computing the solution is actually building on the 2 steps of the proof. So now we move on to computing the market equilibrium. The first step is to compute the trip assignment problem. And the first step, so here is a network. It is series parallel. You have these edges that talk about the time cost as well as the capacity. So now the network is initialized to be empty. The shortest path is taking E1 and then E4, right? So this has a time cost of 2, and capacity equals to 2. So I'm saturating this route. I'm giving 2 lanes of this route comprising of E1 and E4. And because the time is 2, and I kind of set the time interval to be from 1 to 4, capital 4, I have 3 time slots of the departure time for this route. And second, so now this route, these 2 edges are removed from the network because they no longer have residual capacity. So then I move on to the next route that has the shortest path, which is E5. And then I'm selecting E5. It takes capacity of 1, and it takes time 3. So I have time slot of 1 and 2 for using this route. And I proceed using the greedy algorithm to select the next shortest path, and then I saturate. And until this point, I look at the previous network. It no longer has residual capacity of the edge, so I stop the algorithm. And it will stop within E number of iterations because in every step I saturate at least 1 edge. Okay. Does that answer your question?
Yeah.
Great, thank you. Yeah. Okay, so this is the first step. I construct this restricted way of sending flows, the route as well as the time slot. And then I start to assign riders to these slots. I construct this auxiliary economy, and then I'm taking the allocation algorithm iteratively in 2 parts. So this algorithm is adapted from the Causal-Crawford algorithm of solving the combinatorial auction theory. Well, the caveat is that because we need to compute the augmented trip value function, and it's actually non-trivial to iteratively update that. So we need to be careful on how often or how we do this update. But based on these 2 pieces, we have an allocation algorithm that can solve how we assign riders to these route and departure time slots. And that actually gives us the socially optimal trip organization. Well, and then we employ the first theorem on the primal and dual relationship. We find that we use a separation-based linear programming approach to solve the dual problem that will give us the toll price as well as the limit. So the separation-based problem requires us to be able to quickly find a violated constraint in a dual problem, and that actually, again, uses the property of Gauss substitute. But I won't talk about the detail there. Okay, so we looked at equilibrium existence under those 2 conditions. We also looked at how we can compute a market equilibrium. There may be multiple market equilibrium because one socially optimal solution can be supported by many payment and toll price edges in a dual program. The platform wants to implement a particular market equilibrium such that no rider has incentive to misreport their parameters. And here, we need to consider finding the VCG equilibrium. So Vickrey-Clark group equilibrium. So in this equilibrium, is such a market equilibrium such that every rider will pay for their social externality. And under this payment structure, riders will have no incentive to misreport their preference parameters. We also find a very interesting fact about it is that actually this particular market equilibrium compared to all the other equilibrium, the riders actually achieve the highest utility. And the toll price is set to be the minimum compared to a market equilibrium that is not strategy proof. The proof of this result actually still builds on the two-step theorem proof, but we need to explore the lattice structure of the equilibrium utility set. So basically the optimal solution of the dual problem has a lattice structure, and one of the extreme value is the value with this payment structure. Okay, so we draw ideas from combinatorial object theory and quickest network flow problem to look at the sufficient conditions of existence of market equilibrium, algorithms for computing the equilibrium, as well as looking at strategy proofness and whether or not riders' utilities are maximized. Some interesting theoretical extension includes, can we look at approximate market equilibrium, where people may roughly have the same homogeneous carpool disutility, but it is not exactly the same. But people are also willing to stick to the assigned trip as long as the deviation does not provide too much of profit. Second is, what happens if riders actually arrive at a platform in an online fashion? Can we find online algorithms to execute this carpool market while also respecting the dynamic network capacity constraint? The third is the logistics. It's more broadly the logistics and pricing problem with autonomous shared mobility. Well, just to talk about, so this wraps up that paper, but just to talk a bit about one of the numerical, I have how much time? Okay, I have 2 slides. So it's the empirical work of actually computing the toll price. So this is joint work with one undergrad from Oregon, one undergrad from Berkeley ECS, and 2 PhD students as well as Professor Shankar Sastry from Berkeley ECS. So here we used a bunch of data sets to look at how we compute the toll price of these bridges in Bay Areas. We use these data sets to estimate and calibrate network cost functions. And more importantly, we want to estimate people's willingness of pay. Because in my theoretical work, I focus on people actually have different value of time. This is the heterogeneous preferences. And heterogeneous preferences make the marginal toll price do not work because people take the marginal toll price differently. And we use inverse optimization to estimate their willingness to pay for the toll, and that allows us to redesign the toll prices, which formulates an optimization problem with equilibrium constraints, while with the goal of having the trade-off between minimizing the total congestion as well as to making sure the fairness of the transportation system, so that people with different wealth level, usually have different level of willingness to pay, would share the resource in a relatively more equal manner. Okay, so this is the wrap-up. The research agenda that I have is try to find a framework that incorporates both the human behavior and institution as well as engineering systems that goes from the source of the data to analyze and predict the aggregated behavior to finding the solutions that provides the information and incentive design as well as the market mechanisms to reshape the incentives and improve the social welfare. This includes the modeling of the strategic interaction, the analysis of the behavior as well as the learning processes, the information and incentive design. This is the last slide. I will just stop here.
So there are refreshments waiting for us next door, and we're right at time. Maybe 1 or 2 quick questions, and then we can
So you adopted this series parallel structure, which enables you to get some very beautiful results. When you have real road networks, I guess they always have that kind of Wheatstone structure. Is all hope lost, or What happens then?
Yeah, thank you. So two things. One is that here the toll price is simple. You set toll price on edge, not on route. And you set this toll price called anonymous toll price, which means you do not discriminate or differentiate who is the carpooler. So in this case, so series parallel network is only required when you are doing this anonymous tolling on edge base. Second is that when you have a Wheatstone network, you can come up with a way to allocate the edge capacity to routes. And you say, this is the dedicated carpooling. This is actually what happens on 101. They have the carpool that says from this, what's that called? Off-ramp to the next off-ramp is this much. So they are actually not doing an edge-based toll price, they're doing a route-based toll price, and it's on dedicated price. Yeah. Thank you. Well, it is yet for me to find out how Singapore actually does it. I think they do this anonymous tracking of vehicle and then charge the vehicle based on the trajectory they take, not on edge. Yeah. But I need to confirm that. Yes.
I'm curious, how would the car accidents on the road affect your calibration of the parameters as well as the equilibrium?
You are asking about the empirical side or the theoretical part? So, okay, so the theoretical part is that I'm putting an assumption that the capacity is fixed and does not vary over time. When that is removed as the fluctuation, the theoretical results won't be so nice because actually the quickest arrival flow problem is very hard when you have a time varying network capacity. On the numerical aspect, in the way that I process the data, which is mainly the loop detector, I actually also use the California Highway Patrol data set for incidents. And there I delete all the time slots where there is incident. And we have one work that looks at how the behavior changes with incident-free and non-incident. There is drastic change, and people use BART a lot more when there is a major incident, especially on the bridge. So the behavior does change because your cost function changes.
So I'm going to, in the interest of me making my time slot to pick up my kid, I'm going to suggest that we adjourn now. Thank Manxi again.
Kind of. I mean, I didn't read it, but I sort of. Just like fundamental.